Hello and welcome to this session. Learning Outcome, LO3, Understand Energy Transfer, Forces, and Elasticity. Today, we will explore how forces and energy transfer shape our world, uncovering the principles of work, energy, and deformation, and understanding the mechanics behind stretching, bending, and compressing objects. Work is calculated by multiplying force and distance. Imagine applying 50 newtons over 10 meters. The work done equals 500 joules. This calculation shows energy transferred through force. Understanding this helps in analyzing physical processes. 1 joule equals 1 newton meter. These units represent energy transfer. They are interchangeable in calculations. This conversion simplifies understanding of work done. It highlights the relationship between force and displacement. Hooke's law describes this relationship. Stretching a spring applies a force to return it to equilibrium. Force is proportional to extension. The greater the stretch, the greater the force needed. This concept is crucial in understanding elastic materials. Bending a beam involves complex force calculations. Material properties and geometry are key factors. Engineers use specific formulas for bending. This process is vital in construction and design. Understanding bending helps ensure structural integrity. Compressing an object applies a force pushing back to equilibrium. Hooke's law also applies here. Compression force depends on spring constant and distance. This principle is used in car suspensions. Understanding compression aids in mechanical design. Elastic deformation allows materials to return to original shape. It involves reversible changes. Hooke's law governs this behavior. Energy is stored as potential energy. This concept is essential in understanding material properties. Inelastic deformation leads to permanent changes. It doesn't follow Hooke's law. Energy is dissipated as heat. This behavior is common in materials like clay. Understanding inelasticity is crucial in material science. Elastic materials return to original form. Inelastic materials change permanently. Hooke's law applies to elastic deformation. Inelastic deformation involves complex stress-strain relationships. Recognizing these differences aids in material selection. Elastic deformation stores energy as potential. This energy converts to kinetic upon release. Inelastic deformation dissipates energy. Understanding energy storage helps in designing efficient systems. It is vital in applications like springs and engines. Rubber bands and steel springs exhibit elasticity. They return to shape after force removal. Most metals also show elastic properties. These materials are used in various applications. Elasticity is key in designing flexible systems. Clay and putty show inelastic behavior. These materials undergo permanent deformation. Inelasticity is undesirable in many engineering applications. Recognizing inelastic materials aids in avoiding structural failures. This understanding is crucial in material engineering. Understanding both types is important in material science. This knowledge aids in selecting suitable materials for specific applications. Consider 50 newtons moving an object 10 meters. Work done is 500 joules. This example illustrates energy transfer in action. Calculating work done is essential in physics. It helps quantify energy used in moving objects. Hooke's law applies to springs and elastic materials. Force is proportional to extension. This relationship is linear within elastic limits. Engineers use it to design resilient systems. Understanding this law aids in predicting material behavior. Bending beams requires understanding material properties. Engineers calculate forces using specific formulas. This ensures structures withstand loads. Bending is crucial in bridges and buildings. Mastering this concept is vital in construction. Compression forces push objects back to equilibrium. Hooke's law describes this behavior. Understanding compression aids in designing suspensions. It is crucial in automotive engineering. Recognizing compression helps in creating stable systems. Elastic deformation stores potential energy. This energy converts to kinetic when released. Inelastic deformation dissipates energy as heat. Understanding these conversions is vital in energy management. It aids in designing efficient machines. Choosing between elastic and inelastic materials is crucial. Elastic materials are preferred for flexibility. Inelastic materials are avoided in load-bearing structures. Understanding material properties aids in making informed choices. This knowledge is key in engineering. Elasticity and inelasticity have real-world applications. Springs, bridges, and buildings rely on these principles. Understanding forces aids in designing resilient structures. This knowledge impacts everyday life. It ensures safety and efficiency in engineering. In conclusion, we have learned that forces and energy transfer play a fundamental role in shaping our world. Understanding how materials deform is essential in engineering, as this knowledge enables the design of more efficient and effective systems. Should you have any questions, please contact us on 0748436168. Our team is always happy to help. Thank you for your attention. See you next time.